In today's video lecture, we will continue to work on the capacitor inductor note packet. Today, in particular, we're going to introduce the second device, the inductor. What we're going to see is that in many ways the inductor parallels the capacitor. All the different properties that we saw with the capacitor, we're going to see that we have similar properties with the inductor. However, what we will see is that these properties, although similar, are in many ways exact opposites. And one of the things we're going to focus on is how the inductor and capacitor are similar and how they are in many ways opposite devices. Before we introduce the inductor as electronic device, we need to understand the more general concept of inductance. You might remember from physics classes in high school that if you have a conducting coil, in other words, a coil with current flowing through it, it gives rise to a magnetic field. That's what these curved lines represent. This property is known as Ampere's law. The amount of the magnetic field that actually goes through the loop is called the magnetic flux linkage, and it is given the Greek symbol lambda. This is the Greek letter lambda. Turns out that this magnetic flux linkage is always going to be proportional to the current flowing through the coil. The more current you have, the stronger this magnetic flux linkage is. The ratio between the magnetic flux linkage and the current is what we call inductance, and we give it the letter L. The unit of inductance is the Henry, capital H, and 1 Henry is defined as 1 volt-second per ampere. At this point, you really don't need to understand the electromagnetic properties of the inductor. I just introduced this here so you have an idea where it comes from. But anyway, as you see in this picture here, if you have a coil with a current flowing through it, you can sort of see a little bit with these little shavings. These are shavings around here. You sort of see a little bit that the shavings are concentrating themselves in line with these magnetic fields. One of the properties then is if you take a coil of wire and add multiple turns, it actually increases the strength of this magnetic field. Specifically, it increases the strength of the magnetic flux linkage, which creates an even stronger relationship or a larger inductance. And this is the idea behind the inductor, as we will see on the next page. So the inductor is covered in section 6.1 of the book. I should mention that the inductor is also called sometimes a coil, and it's sometimes also called a choke, especially if it's used in a power supply. And it's called a choke because it chokes high frequencies, as we will once again see very soon. So the way an inductor is created is you take a wire and coil it around itself like that. That, as we saw on the previous page, concentrates these magnetic field lines and creates a strong flux linkage. Not surprisingly then, the schematic symbol for an inductor is going to be a coil, like that. One of the electromagnetic properties says that if you now change the applied current, that in turn is going to change the magnetic field and change the flux linkage, which is going to induce an electric field. This is Faraday's law, which is closely related to Ampere's law. That in turn gives rise to a voltage drop across the inductor. So once again, we're going to see that changing the current gives rise to a voltage. Just like we saw that in a capacitor, changing the voltage gives rise to a current. Another parallelism between capacitors and inductors is that they both temporarily store energy. An inductor stores the energy in the magnetic field, just like the capacitor stored it in the electric field. Let's look at some equations involving the inductor. So we know from the previous page that inductance is flux linkage divided by current. So flux linkage is inductance times current. If we now take the derivative of both sides from Faraday's law says that voltage is the derivative of the flux linkage. This is what Faraday's law is stating. So the voltage across the inductor is the derivative of the inductance times the current through the inductor. The inductance is a constant, it comes out of the derivative, and we end up with the relationship that the voltage across the inductor is the inductor's value times the derivative of the current. Once again, compare that to the current through a capacitor is C times dVc dt. For an inductor, it's VL is L dIL dt. So once again, similar but opposite. Like the case of the capacitor, you can express the IV relationship in integral form and say that the current through an inductor is some initial current at time t0 plus 1 over L times a definite integral from t0 to t of VL tau d tau, where tau is a dummy variable. Once again, just like with the capacitor, we see two more points here. One is that this term here provides memory to the circuit because it gives some history about prior current values. This is going to be a key thing with inductors, just like a capacitor provided memory to the circuit. The other important point here is that from this relationship up here, we see that if the current were to change instantaneously, di dt would be infinite, which would give you an infinite voltage, which is not possible. So the second point here is that the value of the current through an inductor cannot change instantaneously. Just like in a capacitor, Vc cannot change instantaneously. So once again, similar property, but opposite property. And we use the same notation we used with capacitors with this little minus sign here and this little plus sign here. What this is saying is that the current through an inductor at an instant before some time t0 is going to be the same as the current through the inductor at some time right after t0. Let's look at the inductor in DC steady state. We talked about DC steady state with capacitors, if you recall. That's saying, suppose you have some voltage or current that's been there a long time and it's constant. In steady state conditions, the inductor current is going to be a constant. If it's constant, its derivative is 0, which means the voltage across the inductor is 0, so the inductor is modeled as a short circuit. So if you have this situation on the left here, you have a current source. That current is partially going through this resistor. Part of it is going through this inductor instead. After a long time, so after we reach what we call DC steady state, the inductor looks like a short circuit. Once again, compare that to a capacitor. In a capacitor, it is a DC open circuit. An inductor is a DC short circuit. Let's look at a very simple example. Let's say that we have a 10 volt source going through a 10 kilo ohm resistors and there's a switch. So initially we have that connected to an inductor. So it's going to cause current to flow. What we want to do is determine what happens to the current Ix that's through this branch here once the switch is thrown and that's connected that way. Well, at t equals 0 minus, this is right before the switch is thrown. We're assuming it's been sitting this way a long time. You have a 10 volt source, a 10 kilo ohm resistor. The inductor is a DC short, as we saw on the previous page, and the current IL from Ohm's law is 10 volts over 10 kilo ohms, or 1 milliamp pointing down. At t equals 0 plus, right after the switch is thrown, now The switch connects the inductor to this wire with this current Ix defined as that current there. IL is still defined as that current there. IL at 0 plus is the same as IL at 0 minus, so it's 1 milliamp. So Ix is going to be negative 1 milliamp. Once again, negative because the direction of Ix is counterclockwise. The direction of IL is clockwise. What would happen then is this would continue to flow. The inductor does not dissipate any energy, and there's no resistor in the circuit, so this current would continue to flow forever. The second part of the question then says, what would happen if there is a resistor in this branch? By this branch, I mean this branch right there. If a resistor is present, now we have this situation. Once again, this is for t greater than 0. Well, IL of 0 plus is still 1 milliamp, but the resistor will slowly use up the energy that is stored in the magnetic field of the inductor. So in this case, eventually, the current dies down. A good analogy for all this would be a water wheel. A water wheel is a good analogy for an inductor in the sense that for the inductor to build up this energy, it needs to have some external force that creates the current, connecting it up to a voltage source, a current source, etc. Likewise, a water wheel needs to have some external device to pump water into the water wheel, whether it be coming from a creek or a river or a pump, whatever. Anyway, as the water wheel builds up momentum as the water goes through it, it's storing energy. It's storing energy in that water wheel. Then, even if you turn off the source of the water, guess what? The water wheel is still going to turn for a while. Eventually, friction will cause it to slow down and stop, but not right away. Inductor is the same way. Before 0, we are through this voltage source. We're providing current to energize the inductor. At t equals 0, we are removing the voltage source, but if there's no resistor here, such as in this example down here, that current's going to continue forever. If there is a resistor, as in this example on the right, eventually the current will die down. Let's look at the inductor in AC steady state. We looked at AC steady state for capacitors. Now we're going to look at it for inductors. So let's assume that the current through an inductor has a magnitude of I sub L, a frequency of omega, and a phase of phi. We know that the voltage across the inductor is L times the derivative of the current through the inductor. We know the derivative of a cosine is a negative sine. We also know that the frequency within the cosine comes out as part of the derivative. We also know that negative sine of x is equal to the cosine of x plus 90 degrees. We saw that when we looked at the same thing with capacitors. And so this expression here can be rewritten as this one. We can now look at two things. The first one is the phase angle difference between the voltage across the inductor and the current through the inductor. So the current through the inductor has an angle of phi. The voltage across the inductor has an angle of phi plus 90 degrees. We say that the voltage across the inductor leads the current by 90 degrees, or the current lags the voltage by 90 degrees. And sure enough, if you look at the figures on the right, you'll see that the voltage waveform peaks a quarter period or 90 degrees earlier than the current waveform. The more interesting property, however, is with the magnitude of the voltage. So we're applying a current with a fixed magnitude. What happens now if you change the frequency, of the input, what happens to the amplitude of the voltage? We see that the amplitude of the voltage changes as the frequency of the current changes. So for an inductor, the amplitude of the voltage is frequency dependent. Specifically, we see that the magnitude of the voltage is equal to omega L times the magnitude of the current. So unlike a resistor, but like a capacitor, the voltage-current ratio is not the same for all frequencies. For an inductor, the voltage-current relationship, which we can call resistance, in quotes if you want, because it's not really a resistance, the magnitude of the voltage divided by the magnitude of the current is omega L times IL over IL. These cancel, and we get omega L. Once again, if you compare that to a capacitor, in a capacitor, the magnitude of the voltage to the magnitude of the current was 1 over omega C. That means that inductors and capacitors are both frequency-dependent resistances, or impedances as we more properly state. The difference is, in an inductor, the omega is in the numerator. In a capacitor, the omega is in the denominator. That means that for an inductor, as you increase the frequency of operation, the resistance increases. In a capacitor, as you increase the frequency, it decreases. Another similarity between capacitors and inductors is they both temporarily store energy. They do not dissipate power, they do not generate power, but they can temporarily store energy and release it later. The difference, once again, is a capacitor stores energy in an electric field. The inductor stores its energy in a magnetic field. The equation for the stored energy is very similar. All the work is shown here on the right. You really don't need to worry about that. What's important is the final result. The energy stored in the inductor at any time is 1/2 L times IL squared. Once again, compare it to capacitors. For a capacitor, omega C was 1/2 C times VC squared. So similar equations, but certainly not identical equations. Now we're going to look at an example that ties together some of the concepts that we've learned about capacitors and inductors. If you look at this circuit, it looks sort of complicated, but it actually is a very simple problem, as you'll see. So we're told that this voltage source has been activated a long time, and we are asked to determine the energy stored in each of the capacitors and each of the inductors. Remembering the capacitors store their energy in their electric fields and the inductors store their energy in their magnetic fields. The key words in this problem is that the voltage source has been activated for a long time. That is basically telling us that we are in DC steady state. Whenever you are in DC steady state, what we're saying is that the capacitor is fully charged so that there is no more current flowing through it. It's an open circuit. And that the inductor is fully energized, which means there's no voltage across it, and it is a short circuit. So the first step is to redraw the circuit. in DC steady state. The voltage source is unchanged. This resistor is unchanged. This capacitor becomes an open circuit. This inductor becomes a short circuit. This resistor is unchanged. This 1200 ohm resistor is unchanged. The 2 microfarad capacitor looks like an open circuit. The 500 ohm resistor is unchanged. This 9 millihenry inductor looks like a short circuit. And finally, this 200 ohm resistor is unchanged. Let's label now the voltage across the 1 microfarad capacitor. We'll call that VC1. The current through the 3 millihenry inductor we'll call IL2. The voltage across the 2 microfarad capacitor we will call VC3. And finally, the current through the 9 millihenry inductor we'll call IL4. So important things here, the 2 capacitors are modeled as open circuits in DC steady state, and the 2 inductors are modeled as short circuits in DC steady state. Before we try to find VC1, IL2, VC3, and IL4, we want to simplify the circuit a little bit more. So if you think about this a little bit, think about this branch. The 500 ohm resistor has no current flowing through it because it's in series with a capacitor which is open circuited. So basically, it's like this branch isn't even there. No current's going to flow through that 500 ohm resistor, so it really doesn't affect anything on the circuit. Likewise, on the far right, if you look at this branch, it's in parallel with a short circuit where the 9 millihenry inductor was. So likewise, no current's going to flow through that 200 ohm resistor, so it's like it doesn't exist at all. So we could get a simplified version of the circuit that looks like this. We still have our variables VC1, IL2, IL4, and VC3 is now that voltage. The VC3, if you don't see right away, you might say, well, wait a minute, VC3 is a voltage drop between this point and that point there. This point up here is the same as that, voltage-wise, because it's connected by a wire. If you think about this point here, because no current is flowing through the 500 ohm resistor, the voltage here is the same as the voltage here. So the voltage across the 2 microfarad capacitor, VC3, is the same as the voltage across this inductor here. That's why VC3 you can write like that. Once you accept the fact that this circuit on the right is the same thing as the circuit on the left, which in turn a model of this circuit in DC steady state, once you've accepted that, we can now actually analyze this. So let's actually redraw the simplified circuit diagram. We have a 5-volt source, 100 ohm, 600 ohm, 1200 ohm resistor. We don't care about the other 2 resistors, and our variables we're solving for are VC1, IL2, VC3, and IL4. And for convenience, let's put ground there so that the voltage at this node up here is VC1. So we want to use some circuit analysis technique to solve for those variables. Because I like nodal analysis, I'm going to sum the currents leaving the VC1 node. Current going to the left is VC1 minus 5 volts over 100 ohms. Current going down is VC1 minus 0 volts over 600 ohms. Current going to the right is VC1 minus 0 volts over 1200 ohms. The sum of those currents is equal to 0. That simplifies to VC1 times 15 over 1200 is equal to 5 over 100. Solve for VC1, you get VC1 is 4 volts. That means that the energy stored in the first capacitor is 1/2 times the capacitor value, which from the previous page is 1 microfarad, times the voltage across the capacitor squared. You get 8 microjoules. For the energy in L2, we could use Ohm's law to find that current. So from Ohm's law, the current IL2 is this voltage divided by that resistance. So it's VC1 over 600 ohms, which is 6.67 milliamps. That means that the energy stored in the second inductor is 1/2 times its inductor value from the previous page times its current squared, 0.0667 microjoules. For the second capacitor, because VC3 is equal to 0 volts, there's no energy stored in that second capacitor. Finally, we can use Ohm's law again to determine the current through the second inductor. IL4 is equal to VC1 over 1200 ohms, which is 3.33 milliamps. So the energy stored in that inductor is 1/2 times its inductor value times the square of its current, which is 0.05 microjoules. So this problem illustrated DC steady state, what to do with the capacitors, turn them into open circuits, what to do with inductors, turn them into short circuits, and this problem also illustrated how to use the energy equations to find the energy stored in the 4 components. Remembering in the capacitors, the energy is stored in the electric field, and in the inductors, the energy is stored in the magnetic fields. We will pick this set of notes up with the next lecture. See you later.